So, okay, we're going to try something a little different. So I'm going to record these and like show some, go between dock camera and PowerPoint. So bear with me. Especially because we need to spend some time on polarity, but I don't know how much time we're going to spend, so it might go off slide for as we need be. So, last chapter we looked at the idea of a bond dipole, but the basic idea that if we have a difference in electronegativity, a difference of attraction of electrons, that an individual bond can see a difference in charge. It's not as big a difference as, say, a ionic structure where we have a full cation and a full anion, but it is a very real charge there. And it's really easy to see if you just talk about, say, a carbon hydrogen bond or a carbon fluorine bond or OH bond. But when we think of the whole molecule, we have to think about how all of the bonds fit together. And that's where we get what's called a molecular dipole. So we're asked, can we imagine a scenario in which a three-dimensional molecule adopts a region of positive and negative around itself? This positive and negativity allows us to essentially create a region of attraction between various things. In order to do this, to properly do this, we need to understand the idea of vectors and opposing forces. The basic premise here is that if I have an attraction that is equal and directly opposite, they cancel out. The basic idea being, if in like a tug of war, if you have two sides of equal strength, if nothing goes to break the tie, one side is pulling the electrons one way, one side is pulling the electrons the other way, and they end up canceling out. Even if the individual bond, you would say, is polar, if the net result is they're equal and opposite, they cancel out. So I just want to jump to the dock camera real quick just as an example. So like if we in a structure like this molecule, even if the yellow to red bond is particularly polar, where you would call this a very polar bond, because this guy is pulling equally the other direction, this doesn't move one way or the other. We need a difference for this to move one way or the other. If I switch this for a different atom, if these are both oxygens, they cancel out. But if I remove an atom, suddenly we have a very polar structure. If I put this on, they cancel out. I'm going to draw on here real quick. Two examples. C double bond O. C. This in itself, that is, both of those are polar. But one is pulling to the right, one is pulling to the left. So the net effect is they cancel each other out. It's a non-polar molecule. CO2 is particularly non-reactive with many things because of that. It's not polar. It wants to be polar, but it's not, so it extinguishes our fires because it doesn't really react. It's like nitrogen. But if I simply make a carbon monoxide, that's also a polar bond. And so we end up having, we can say like, oh, there is a region of electron density that is pulled in this direction. And this then becomes, hey, this can now react with molecules. Carbon monoxide is particularly reactive because of its polarity. And this carbon monoxide readily binds to our iron in our hemoglobin. Oxygen binds to the iron in our hemoglobin. And so oxygen binds reversibly, meaning it binds to the iron, the blood gets delivered to where it needs, the oxygen is released, and it can keep doing that. Well, carbon monoxide binds stronger. So if it's sticky, it sticks to our red blood cells, and then we have a hard time getting rid of it. And because it's blocking our blood cells, we can be inhaling a bunch of air, but we've essentially been poisoned with carbon monoxide. So it doesn't take a lot to kill us, because if it sticks to enough of our blood, we're just essentially deprived of oxygen, even if we're in pure air. I'm trying to think. Don't quote me because I'm not a medical professional, but I think one way they cure that is I think they have to flush with highly enriched oxygen. So it's not just air, but like pure oxygen. If you have enough of it, it will slowly start to displace the carbon monoxide. But it's not a fast process, and not very easy, so we need to move it. Now, water is polar, because even though there's two things coming off of water, when we make the water structure, when we draw this, we think of it as bent. Why? Because it is tetrahedral. And then, so even though this is pulling right and left and up, this guy's pulling right and up. They may be pulling left and right, and those do cancel. But what are they both pulling? They're both pulling upwards. If they're both pulling upwards, the net effect is an up dipole. So you can imagine if I split this molecule in half, the top half is negative and the bottom half is positive. And as long as there's two halves, one negative and one positive, we have a dipole. As long as there's two halves, one negative. This guy, you could not split this guy in half. You couldn't split it in half this way. You couldn't split it in half this way, because the top half or the bottom half is not favored one way or the other. So something we got to think about, something we got to keep in mind. I'm going to go back to the slide for now. But so now we have to think of our vectors in a three-dimensional XYZ coordinate. Now, do you need to understand the really in-depth math? No. If you can see the symmetry, you don't have to worry about the vectors. But if people are mathematically oriented, they can picture these vectors and imagine vectors add. Like a vector is a force and a direction. If I have a force going left and a force going right, and the forces are the same, it doesn't move. But if the forces are not equal, things move. A bunch of football players grab chains and start pulling against a truck that's going the other direction. If the football players are stronger than the car slides backwards. If the car is stronger than the football players, they start being drug along. It's all about the strength and the directions. And as so long as they do not cancel out, we can have a polar molecule. But whenever they cancel out, we get a nonpolar molecule. One of the big things is symmetry. The key feature here is symmetry. Whenever you have what's called a symmetrical molecule, when you have high degrees of symmetry, these guys are nonpolar. when you have asymmetry, which means a break in symmetry, suddenly we have the possibility for a polar molecule. So I'm going to make some models and show them on the screen and see if we can see the symmetry together. So, and I have some on the next slide as well we'll look at, but I think hopefully being able to pass them around will help us. Actually, I'll go ahead and go to the next slide first, and then we'll spend some more time. So, the above structures are all asymmetric in one way or another. So this one is just a single HCl bond. The green is the chlorine, the hydrogens are white. Chlorine is electronegative, hydrogen is not. And so the hydrogen gets its electron density stolen. That's pretty simple. We don't have to really think about that. Now the water. There's the water. Water's oxygen is red, so H2OH. So we don't really have to think about that too much. I'll show that more. And this guy is chloroform. Not chloroform, but dichloromethane. It's carbon, hydrogen, hydrogen, chlorine, chlorine. There will be symmetry here. There is symmetry, and I'll try to show this in a minute with actual model. There is also a break in symmetry. There's a bunch of breaks in symmetry, and when you lose symmetry, this becomes the potential for being polar. So now the structures on the bottom all cancel out. CO3, carbonate. That's a trigonal planar shape. That is highly symmetric, and I'll try to show that to you in a second, and they all cancel out. SF6 on the bottom right, they all cancel out. These guys are highly symmetric. CO2, highly symmetric. So let me try to show some of these, and I want you to try to see these, and then I can pass them back for those in class. But so this is our dichloromethane. You can imagine if I hold this right here, a mirror plane cutting it right in half, or a mirror plane cutting that right in half. And if I do that right, I'm reflecting the chlorines on each other. So that's symmetric there, that's symmetric there. But it's not symmetric if I hold it right here. If I cut it right in half there, I have my two chlorines. I have my two chlorines on the left, two hydrogens on the right. They don't cancel each other out. The chlorine and the hydrogen are not equal. These guys are pulling one way. These chlorines are pulling the other way. They're not the same. Water. Yes, I can cut it in half right here. I can cut it in half right here, but I cannot cut it in half I cannot cut it in half right there because the top half and the bottom half are not the same. So I want you to look at this. This one's the easiest to see all the symmetry in. The SF6, you can imagine the top and the bottom being the same. They cancel out. These two guys cancel out. These two guys also cancel out. And these two guys also cancel out. But these molecules are highly symmetric. Notice how if I spin this really fast, which guy was the top? Do you know which guy was the top? I mean, maybe if you're watching this at home, you could record this and fact like, oh yeah, it was that guy or whatever. But if they're all the same, they all are more or less equal. I could rotate this all sorts of ways, and you don't know where we started at. But if I take one atom off, these two guys still cancel. These two guys still cancel. But where is this guy's pair? His pair is gone. Suddenly, this guy is we lost a plane of symmetry, so suddenly it's could be polar. But if I take another guy off, these two guys are equal, these two guys are equal. It's back to being highly symmetric again, and so now they all cancel out. If I remove a third atom, it's T-shaped. These two guys are equal, but this guy has no match. So, back to being polar. This is your basic tetrahedral shape. Once again, vectors. You want to say that there's clearly we have one guy pulling up, one guy's top, and three guys pulling down. Should not three guys beat one? We want to say that. That want to be the case. But if we look, this guy is pulling directly up. It's only in the up direction. These three molecules are pulling at an angle. And this is where the vectors come into effect. That essentially, while one guy has a vector that's straight up and down, one guy has a vector that is both at an angle that is in the x, the y, and the z, as opposed to just the z. So if you calculate this from the z from a triangle perspective, this is much smaller than this. And so when we add up all three downward guys, they end up canceling out one upward guy. And how can you justify that in your brain? Well, once again, let's do the spin test. If I spin this over, which guy was the up? Which guy was the up? Do you know which guy was the up? If you do not know which guy was the up, how can we say this guy was the weakest? If I rotate a bunch of people around and they're all wearing masks and they're all wearing the same masks and you don't know who is who, how can you say this guy it will definitely be the winner or the loser? We don't. Because if I rotate this guy, boom, right here, the dipole should not change when we rotate an atom. If up always wins or up always loses, then if I rotated this, then this direction should still be losing. But if they're always if they change, that's where it comes into effect. That's where we have to think about it. So if I switch one atom, suddenly you can say this guy is very much so different from these guys. If I rotate it, well, there he is. Orange guy's still here. Orange guy's still here. If the orange guy wins every time, then you rotate it, the dipole is going to stay with the orange guy regardless of how it's viewed. So if I flip it upside down, orange guy's on the bottom, the dipole's still on the bottom. Dipole's now on the top. The dipole's on the right. So the silliness of this is if you can see all these symmetry elements, then that is how these guys actually take effect. This is how these... I've got to find... I want to show you the trigonal planar one real quick. I want to show you the trigonal planar, that how this one's even... This one's also easy to think, oh, shouldn't this be polar? But vectors say no. We have right here three guys. One is pulling straight up and two are pulling down. You want to say two guys are stronger than one. However, these guys are pulling down and at an angle, so their net attraction straight down is only so they are pulling here on the hypotenuse, but this part of it is exactly 1/2 of the straight up. So if I rotate this guy, rotate it, You don't know. Now we have a new guy up top. Now we got a new guy up top. And if we can rotate them, they are the same. And if they are the same, they cancel out. So I'm going to draw our basic structures, and we'll mention this in lab next week. But these guys are our highly symmetrical structures. I'll bring it up again in lab. If we have these structures and all of the outer atoms are the same, then these can never, ever be polar if all the x's are the same. And that is because of the large amounts of symmetry present. I'm just drawing these are our base structures. And there's 2 more. Or 3 more, really. No, 2 more. So then we have our x. So these structures. And then our linear. Lone pair. So linear are trigonal planar, are tetrahedral, are trigonal bipyramidal, middle, and are octahedral. Those are our base ones, octahedral, and square planar. If all of the x's are the same, if they're all the same, these guys can never, ever be polar. Alternatively, if the center atom is the same as an outer atom, or the center atom is the same as all the outer atoms, this cannot be polar. This is not a polar bond, because I cannot beat I. But if I put I and an F together, suddenly they're different. These guys are different molecules, different atoms. They can be of different strength. You put 2 linebackers who can lift the same and push them against each other, they're going to not move. But you take the linebacker and the QB, well, the QB is probably going to be toppled over. You got different strengths of atoms. So whenever we have differences, we can be potentially polar. But if there is no differences, or there is high symmetry, polarity is not likely. And so we have non-polar structures. So that's one of those things. I often ask on the test, draw a structure that is polar and one that is non-polar. Say, like, for example, a square planar thing. A square planar. So Rn, I've asked this one in the past. Rn, Cl, Cl2, Br2. Draw one so the basic structure will be Rn, lone pair, square, it's going to be a square pyramidal, a square planar. Now, how do we differentiate polar from nonpolar? Polar from nonpolar is one where not equal when opposite. And then nonpolar would be equal and opposite. So, and opposite. So the key here being, I have to put 2 chlorines on. I have to put 2 bromines on. Wherever I put chlorine, the other chlorine must go opposite of it. Wherever I put 1 bromine, the other bromine must go opposite. And because they're opposing each other, this guy beats this guy. It doesn't matter how strong chlorine and bromine are versus each other. If they never get to compete against each other, it doesn't matter. But so this one, wherever I put the chlorine at, if I put a bromine there, now suddenly we have a competition. If I put the other chlorine, it doesn't matter whether I put the other chlorine here or here. I put the bromine there. Now suddenly we have a competition. So now we suddenly have a polar molecule where I can split this in half. Or this half is going to be negative, and this half will be positive because chlorine is stronger than bromine. Now, am I expecting you to know which one is stronger, chlorine or bromine? Not without a chart. Not without a chart. But if you had a chart, you'd look up this guy. This guy is 3. This guy is, I don't know. I can't remember this one. Was it 2.4 or 2.8? Whatever. It's not 3. It's less than 3. And so this guy is stronger. And so it wins in the end. So if you can see these symmetrical elements, you can imagine, you can see whether this is going to be polar or not. So, as I said, symmetry is something that a lot of people have difficulty grasping, which is why spending 30 minutes on like literally 2 slides, that missing like half to or so of the class. But okay. So, with that in mind, now the last half of the chapter, some of which is not going to be really tested on, but it's a lot more theory here. This first half was all about making models and understanding how atoms arrange themselves in 3D space. We're getting into theory of why they try to arrange themselves in the way they do, and what is going on with our magical s orbitals, our p orbitals, our d orbitals, and what have you. So we're going to get into what's called valence bond theory. Valence bond theory, valence bond theory is where is how we explain why the Vesiper models form. The idea here is that it all comes down to overlapping energies in the right way. That when we have to put electrons together, we have to spin pair them where one's spinning left and one is spinning right, and they create their own little magnet that sticks them close enough together. That we reach a maximum energy stabilization. That you can see the chart over here, that as atoms approach each other, the attraction between the nuclei and the electrons reaches a low point. That lowest point is the ideal energy stabilization. If we get too close, the nuclei start to repel each other again. Basically, the positive charges in the center try to fling them apart. It's what keeps atoms from falling into each other. The nuclei want to push each other away. So when we reach a local energy minimum, so we got 2 electrons that might be spinning in the same direction. One of them flips, and suddenly we can pair these guys together. Now, it's even possible for a lone pair on one atom to share both electrons with an empty orbital on another atom in what's called a coordinate covalent bond. This is how many metals bind with things. Metals are typically positive guys that don't have a lot of electrons. So there's many atoms that have lone pairs, and they're saying, here, you can borrow these right now. Yes, I know they're mine. I'll get them back later, but you can borrow some of my electrons to stabilize yourself. So many compounds that metals form in water come from this lone pair donation. But so this picture works reasonably well for simple things like H2 and HCl. You can imagine H2, two s orbitals overlapping. That's what we see right there in the C. Or a p orbital on chloride and an s orbital on H overlapping. And there's the overlap where the electrons are spending time close to both atoms. That works very well for these guys. But it doesn't work for any other, not really any other atom. If we used that logic for water, every p orbital is 90 degrees to another p orbital. 90 degrees. Keep that in mind, 90 degrees. So if we tried to do that with water, you would have to form a 90-degree bond angle because of the sheer nature of the p orbitals. But we actually see a bond angle of 105. So I don't care that you know 105. I'm not asking you to memorize 105. Just know it's not 90. It's much wider than 90. So the p orbitals are doing something weird. That's because what we actually form is a hybrid orbital. We form a mixture of orbitals together that are able to make and adopt new locations. They're essentially stretching their legs so that they can reach different places. So we're going to combine an s orbital with a p orbital. Sometimes many different p orbitals. Occasionally we'll mix s and p and d orbitals together to make new hybrid orbitals. So if I take one s and one p together, I make two new orbitals from those two I used. If I take one s and two of the p's, I'm going to make three new orbitals because I used three. So I'm going to make equal number of new hybrid orbitals depending on how many orbitals I have to use. But it's like I'm mixing them together, like aka the fly, or I'm making a human fly hybrid. Or maybe you're, I don't know, Guardians of the Galaxy 3, making all the human animal hybrids. So we're hybridizing orbitals in order to stabilize these. These new orbitals are named according to how many and what type of orbitals they use. But these guys have newish shapes and can adopt new shape. Well, can adopt new positions to minimize electron repulsion. When we make hybrid orbitals, they are degenerate in energy, which means if I make, instead of an s orbital which is low energy and a p orbital which is high energy, I get two new orbitals that are both equal but mid energy. So I take a low energy and a high energy and I get an averaging of the two, depending on, or three or four. So but they're all the same energy. While this does cost energy to do, we often spend a little bit of energy to get rid of the low energy orbital. We get better outcomes. So here's the basic one. Here's the simplest one, that hybrid orbitals. So our carbon has electron configuration that makes up its electron configuration right here in the upper quadrant shows we only have two unpaired electrons. if we need unpaired electrons to make bonds, it should only be able to make 2 bonds. However, we know based on our Lewis structures that it makes 4 bonds. So what does it do? It takes 3 orbitals from here and 1 orbital from here to make 4 new orbitals. Because they're all the same energy, they can all fit they fit 1 electron each. And so now I have 4 unpaired electrons, each capable of making 1 bond. So for a total of 4 bonds. So what we see is an s orbital and 3 p orbitals make 4 sp3 orbitals. It's like you notice that they're kind of deformed. P orbitals were the barbell shaped. This guy kind of looks like he's only decided to lift with his right arm each time. And so you got one arm that's really bulky, one arm that's kind of like shriveled up. Tries to walk around, he's going to walk around in circles due to the weight differential. Well, these guys are able to arrange themselves into our tetrahedral shape. They're able, because of the minuscule thing of the other lobe, they're able to stick themselves out at unusual angles. Now, because it uses 1s and 3p orbitals, these guys are called sp3 hybrids. So I combined 1s and 3p, and I got an s and p3 that tells us they are sp3 hybrids. Makes 4 of them. Every atom that makes an electron geometry will be sp3 hybridized. Every atom that makes a tetrahedral electron geometry, if it fits into that first column, it's sp3. So CH4, that's sp3. NH3, where it has 1 lone pair, that's sp3. H2O, that's sp3. Because it has 4 things coming off of it, it has to be sp3. Everything that has 4 electron domains is sp3. Now, they could have a different molecular shape, but they all adopt the tetrahedral electron shape. And that's because they all have sp3. I will leave you with that for today. So we only got through slide 15. But we'll look at more examples of types of bonding and different hybrid orbitals and go into a little bit of MO theory. But the rest of that will have to wait. Have a good rest of the break.